All right, so before we move on to improving our model in any way, because it does have some shortcomings, which I addressed in the case when k was positive, and I asked you to address in the case when k was negative. So before we actually go ahead and improve that, I just want to mention a couple other things, 2 or 3 other things that this model is actually really useful for. So the first thing, and all of these different uses, they all sort of hinge upon interpreting what a population is in just other ways. All right, so we did this for a population of living things, bunnies or bacteria or deer, whatever the examples might have been. So we just need to sort of reinterpret what a population could be. And 2 of the most famous ways that this has been done, one of them is to look at it as money in a bank account, and the sort of reproductive rate that's going on, the reproduction that's happening with a money in an account would be under interest. All right, and another very famous way that this has been done is by looking at radioactive isotopes. All right, so the population that you'd be looking at here would be the number or the mass of whatever sample, radioactive sample you happen to be looking at. So you could view it as the mass of it, or you could view it as the number of molecules or isotopes that are in the sample. And the thing that would be happening here would be decay. Right. Responsible for producing 3 new bunnies every reproductive cycle, however long that might last. Well, with the money in your bank account, if you think about how interest is calculated, how it's usually reported is a percentage APR, right? This is typically how it's presented. And if you think about what this means, it's telling you it's sort of an annual, or if it's a credit card, it might be something like a monthly kind of interest rate. All right, so it's telling you how often your money is reproducing, in a sense, right? How often the population of your money is going to change. And the way that they calculate it is as a percentage. And if you think about what a percentage is, it's telling you that the amount of the rate of change of the money in your account is going to be proportional, according to this percentage, to the current amount of money in your account. Right? In other words, if we call A the amount of money in your account, A prime, the rate of change, is going to be proportional, I'll call it R for interest rate, to the current amount of money in your account. And you know how much you invested in there, or how much maybe you withdrew, or you borrowed, I should say, if it's a loan, right? So you know these two facts, right? You've gone out in the wild and you've counted those bunnies, and you know how often they're going to reproduce because the bank tells you the interest rate, right? Just drawing a direct parallel there. All right, radioactive isotopes. This one is, a little harder to see if you're not super comfortable with physics and chemistry. But the general idea is that a certain percentage of your isotopes are expected to decay with time. Now, this is actually, if you want to get into like the really hard math of this, which we're not going to, but if you want to get into the really hard math of this, you actually need some probability and statistics. The reason why is that there's only a percentage chance that any given isotope will decay at any given time. And so, what I'm about to write down is only going to be true on average over a very long period of time. Right? So if you're trying to do radioactive decay models over a short period of time, you're going to see some noise in your data. There will be times when a lot of them decay at once. There will be times when not a lot of them decay at once. And it's a little more finicky if you want to look in the short term. However, on average, over the long-term lifespan of this sample of isotopes, this is how it's going to work. All right, so again, the idea here is that there's going to be some radioactive decay rate that's going to be built in to your isotope that you're looking at. It's going to be different if you're looking at, carbon-14 versus uranium-238 or plutonium, right? These are all going to have different decay rates. But, the idea here is that the mass of your sample, the rate of change of the mass, is going to be proportional, I'll call it gamma, as a proportionality constant, to the current mass of your sample. And you can measure the mass of your sample initially to know how much is there at the beginning. All right, so these are two other examples of how our very simple model can just be reimagined slightly to apply to these two other situations. So, let's look at what's going on here. I asked you to sort of discuss what merit the K-negative case has in our population model. Right, so if we are talking about an actual population, K-negative implies that P of T is decreasing, and if we're talking about bunnies, right, if we're talking about a population of living things, this means that the bunnies are dying. Now, of course, this is like a net effect kind of thing. It doesn't mean that the bunnies are only dying. It just means that their death rate is outweighing their birth rate. All right. So it's like a net effect, not a it's not saying that they're only dying. They are still reproducing probably, but their birth rate is not outweighing their death rate. All right. So this has its shortcomings. All right, this has some serious shortcomings. We do see, the fact that they're dying and that 0 is a fixed point tells us that this limit as t goes to infinity of P of T is going to be 0 in this case, right? Because you can't cross over a fixed point. If you ever proverbially reach the fixed point, it is fixed, so you'd be stuck there forever. All right, so you can't just spontaneously jump over a fixed point and become negative or anything weird like that. So if your population, I'll just quickly sketch the phase plane here. If your population is initially positive, let me draw my K-negative case here. All right, this is P prime equals Kp for K negative. If your population is positive initially, so let's say there's P naught, and this thing, the fact that the graph of P prime is negative when P is positive, this tells you that your flow arrows are flowing back towards 0 because P is supposed to be decreasing because it has a negative derivative. So this means that your population, as time goes on, right, as time increases, your population is decaying. It's going back towards 0. It's decreasing towards 0. And the fact that 0 is a fixed point is crucial here, because you could have something that's positive and it decreases forever, and it just decreases all the way down to minus infinity, right? This is definitely possible. However, that fixed point at 0 tells us that is not possible for our bunny population, because if it ever hits 0, so to speak, it would have to stay there, right? Because it's fixed. Anything that starts at 0 or hits 0 ever stays at 0 forever. That's what that fixed point tells us. So what actually happens here is that we get a sort of condensation, is how you might want to think of it. Everything's going to decay back to 0, but it will never actually reach it. All right, and one sort of quick way to see this is to look at what's happening to the value of the derivative as your population jumps back towards 0. Right, so from this value, your derivative is fairly large and negative. And then you take a jump back, say this is like P of 1 or something, takes a jump back to this first arrow. Well, now your derivative is negative, but it's less negative than it was before. All right, so your derivative has actually gotten a little bit bigger with time. All right, so this is kind of counterintuitive, because you're taking jumps backward towards 0. Your derivative's getting less negative every time you do that. Right? As you jump back towards 0, your derivative's getting smaller and smaller and smaller, which tells you that these jumps are actually getting closer and closer together. Right? So not only is your population decreasing, but your derivative is negative and it's getting bigger. It's getting closer to 0. Right? Which means that your derivative is actually making your population change less and less and less. All right, so what this tells us, just from this very simple picture, what this tells us is that your derivative is going to 0, and that means that your population is changing less and less and less. And the fact that 0 is a fixed point gives us everything we need to know to definitively say that this population is going to decrease to 0, but never actually reach it. All right, so it's not the easiest thing in the world to see this, but I want you to struggle with this fact. All right, see if you can justify this to yourself. Pause the video if you need to, and totally ignore this video for a minute. Take out a piece of blank paper, draw this picture again, and start from scratch, right? See if you can reproduce this exact phase plane portrait that I've just drawn here, without referring back to the video, of course. See if you can reproduce it, and see if you can wrestle with this idea that because P is decreasing, you're hopping backward toward the origin, and that tells you that you're actually hopping along this graph in the phase plane. You're hopping backward, and your derivative is actually getting a little bit bigger. Right, it's becoming less negative. So in quantity, right, in absolute value, your derivative is actually approaching 0. All right. So what that means is that your population is is decreasing, but it's slowing down as it's doing it. Okay. So if this is not clear to you right now, I want you to pause the video, take a few minutes, get a blank piece of paper, and try to reproduce this this logic from scratch. All right, and then come back. So I had you guys do this for homework, but I just wanted to mention one big issue with the model, which is the following, right? This limit as t goes to infinity of our population is going to be 0, and we know that the bunnies are dying off because of this. But because of this weird quirk of the fixed point being 0 and you can't actually reach that fixed point, This means that our bunny population is just condensing at 0. It's approaching 0, but it never actually equals 0. All right? So this is an issue, right? If you're trying to model a population that is asymptotically dying off, right? So as time goes to infinity, you are losing bunnies, right? The population's decreasing. Well, the fact that this bunny population is never going to actually equal 0 means that, quantitatively speaking, you're going to have a hard time determining exactly when this population is gone, right? You're going to have a hard time determining when this population actually dies. And, the reason why is that this population's decaying to 0, right? Will your cutoff be when the population becomes less than 1, right? When P of t is less than 1, is that when you're going to say that the last bunny has finally died, right? Because you can't have half a bunny, right? So that kind of prediction doesn't actually make physical sense as far as a population, exact numbers in a population being predicted goes, right? This doesn't make the most sense in the world. However, you can still use this to make good predictions, right? This kind of idea can still be used to make good predictions. And to see this, let's do the exact same thing we did in the last video, where we take a look at a sort of qualitative sketch of what this graph should actually have to look like. Right, so what we did is we looked at this picture, or the corresponding picture for when k was positive is what we did in the last video. We looked at that picture, and we tried to synthesize all of this information about the first derivative being, in this picture that I just drew a box around, the first derivative being negative, but as we hop back toward the origin, the first derivative actually getting smaller in quantity, right, in magnitude, I should say. It's getting closer to 0. All right, so what this means, right, we know that P is positive. Let me say P naught is positive, right? We know the initial population is positive. Negative bunnies don't make sense. So we know the initial population is positive. From our picture, we know that P prime is negative. And from our picture here, we also know that P double prime, right? So let me just say one word about this before I just make the statement about P double prime. And this is exactly analogous to what we did last video. We know that P prime is negative, but this hopping around on the green graph that I drew here shows that P prime is increasing, right? It's getting closer to 0, meaning it's getting less negative, meaning it's increasing, right? The height is getting closer, it's getting higher on this graph that I drew, right? These red dots are getting higher and higher and higher, meaning that P prime is increasing. And if P prime is increasing, then P double prime must be positive. Okay, I went through this. I had you guys do a lot of pausing and thinking about this in the last video. So here I'm going a little bit faster. So we know that these three pieces of information are all true for our bunny population. P naught is positive. We have some positive number of bunnies. The first derivative is negative, and it is increasing, meaning the second derivative is positive. All right, so what we've got here is some initial population that's positive. Put that on my positive p-axis. And now what I want you guys to do is go ahead and pause and sketch me, or sketch for yourselves, I guess. I can't walk around and check like I usually would. Sketch a graph, just qualitatively speaking, because we don't know any solid exact information, of a graph where P prime is negative and P double prime is positive, and we know this other piece of information. I've sort of drawn a line through part of it here. But because of our fixed point being at 0, we know that we can't actually cross over it or even reach it. So we know that our limit should be 0 as t goes to infinity. All right, so this is like a little Calc 1 problem here. Right? These are really classic Calc 1 problems. All right, go ahead and sketch me a graph, or sketch a graph for yourselves, I should say, that satisfies these three properties. All right, first derivative negative, second derivative positive, and the limit as t goes to infinity is going to be 0. So go ahead and pause the video, take a couple minutes, sketch a graph that looks something like this, satisfying these properties, and then come back. Okay, hopefully your graph looks something like this. Okay, the first condition here says that your population is decreasing, which we've already talked about. The second condition, using Calc 1 language, tells you that your population curve is concave up. Right? Up like a cup, down like a frown. It's what I always tell my Calc 1 students in case you had forgotten what those words mean. And we've got this horizontal asymptote at 0, right? This thing is decaying down to 0. And so your population looks something like this, right? It is decaying, but it never actually hits 0. So let's just have a brief summary here. If we're talking about populations of living things, then the last video I did went through this case when k was positive, and this is like, you know, you can think of this k positive case as being something like corresponding to a net birth rate. For the last homework assignment, you guys did this k negative case, which corresponds to something like a net death rate. And also for homework last time, you looked at the case when k was equal to 0 exactly, and this was really nothing, right? This was the static case. P prime equals 0 in that case, so your population's not changing, it stays constant the whole time. So what I want you to do next, in these two cases that I just mentioned, a reimagining of what a population might look like, the interest in a loan or a mortgage or the savings account that you have, something like this, some kind of interest rate where the population is dollars and cents. I want you to think about which of these situations make sense. Right? Do any of them make sense? Do only one of them make sense? Could you argue that multiple make sense? And I want you to do the same thing for radioactive decay. Right? If you've got some kind of isotope that is decaying over time, think about what should go here. And I used R to represent the interest rate. It behaves the same way K does for the population. And I used gamma for the radioactive decay case. It works the same way that that K does for the population case. I just called it something different. All right, so pause the video, take a second, see if you can fill in these red boxes with bigger than 0, less than 0, equal to 0, right? Some things that might make sense. And then come back. Okay, in the interest rate case, you could, of course, argue that the equal to 0 case makes sense. I probably shouldn't do that in green just to be consistent. Let me do it in gray to be consistent. You could argue that the equal to 0 case does make sense. I would agree with you depending on how you argued it. I might argue something like the, paper money in my wallet right now has R equal to 0, right? It's not growing, it's not decaying, and so it's staying exactly constant. Now, you could, this one's tough because you could also argue that because of things like inflation, and inflation being a predictable percentage change in the value of the dollar, you could argue that less than 0 makes sense for the money in my pocket, right? The value of, say, the $5 bill that I have today is going to be less, assuming inflation rates stay relatively stable, which they don't have to. But assuming that they do, you could argue that the less than zero case makes sense for the money in my pocket, right? It's going to be less valuable. It is going to depreciate in 10 years versus what it is right now. So one could argue that the less than zero case does make sense, and that the equal to zero case does make sense. However, if we are being traditionalists here, if you're talking about interest accruing on money in an account or on a loan, then you are talking about the bigger than zero case. All right, so arguments can be made, and you should try to make them, or you should try to see if you can apply this model to as many situations as possible. But if we're just talking very traditionally about money in an account growing with interest, then you're talking about growth. You're talking about a reproductive rate of your money. And so this is a bigger than zero case. All right, similarly, one could argue that stable elements should have equal to zero gamma, right? The ones that don't decay should be equal to zero because they're not changing, right? Hypothetically speaking. The bigger than zero case, this one's a little weird. You have to know some chemistry, you have to know some physics to talk about the bigger than zero case, right? So you can discuss the bigger than zero case because you can have isotopes that decay to something stable, and that stable element or molecule is going to have a population that is increasing because things are decaying and stabilizing to it. So it's actually growing with time. All right, so you could make this argument. However, if, again, we are being traditionalists here, if we're talking about radioactive decay, then the things we are modeling are only the isotopes that are decaying. Therefore, we should look at the gamma negative case. All right, so this would correspond to a death rate, a decay rate for your sample. Now, in the last video, I talked about how all of this qualitative analysis is all very good at making predictions in a relatively short term. Now, the relative aspect of this is crucial. The three examples I gave you of real-world data in the last video were of, I think, 2 bacteria populations in laboratory settings, and their time scale for the real-world data that the scientists were observing were on the scale of hours. All right, and it was enough over the scale of hours to see exponential growth in, qualitatively speaking, to see exponential growth in these bacteria populations. Then the third graph I showed you was one about deer, a deer population on some island where they didn't really have any natural predators, so they were in kind of an idealized setting. And the deer population only qualitatively looked like our prediction over a scale of something like 3 to 5 years. All right, so it was years in that case. So for populations, you're looking at a time scale where it makes sense, something between minutes, hours, years, possibly decades, could be as high as centuries if you're looking at human development. Interest rates, you're looking at, assuming a lot of different things about finance, which we're not going to get into, you're looking on the order of months, years, maybe decades. Radioactive decay, however, is a totally different ballgame, all right? Just to give you a couple examples of extremes, uranium-235 has a half-life around 700 million years. All right, half-life is the amount of time it takes for half of the sample to decay, on average. Uranium-238 has a half-life of around, I think it's like 4.5 billion years. And if you want a real doozy, Xenon-124 in 2019 was found to have it's theoretically known to have, but it was actually observed decaying for the first time. It's got a half-life around 1.8 times 10 to the 22 years. So that's 1.8 followed by 22 zeros. And just so you have some context, that is 1 trillion times the age of the universe.